next speaker is Seiseki Akibue, Globalness of several events in terms of time and space resources.
Thank you very much for inviting me to such a great opportunity to introduce my research. So I will talk about globalness of separable maps in terms of time and space resources. And my name is Seiseki Akibue from University. And this work is collaborative research with NTT Corporation. And these are contents. So first we concentrate on space resource and next time resource and conclusion. So as we know, LOCC, local operation and classical communication, is not equal to separable maps. So LOCC consists of sequence of conditional, like this, conditional quantum measurements and classical communication of the measurement outcome. I gave an example for LOCC here. Okay, so instead of the clear meaning, clear operational meaning of LOCC, in general, it's very hard to analyze LOCC. So instead of using LOCC, we usually use separable map to analyze LOCC. And I give the definition of separable map. And we can easily check that LOCC, any round of LOCC satisfies this condition. So every LOCC is separable map. And it is known that there are some tasks which are achievable by separable map, but which are not achievable by LOCC. These things. So we can say that there is a gap between LOCC and separable map, and as well we can say that there is a global map in separable map. So we would like to characterize the difference, the gap between LOCC and separable map, or quantify the gap. So conventionally, to quantify the globalness of the global map, we use entanglement. So as we know, if we use pre-shared entanglement plus LOCC, we can implement any global map. So we can quantify the globalness of separable map by using the minimum amount of entanglement to implement some given separable map. And we obtain some result. And we call entanglement space resource, and we obtain some result. In this result, we construct a protocol to achieve 9-state discrimination by using LOCC. And our protocol needs one pre-shared bell pair. And that's not the minimum amount, but it's non-trivial entanglement resource in the sense that if we use one-way LOCC, we need more entanglement. And we also show that for particular discrimination tasks, our protocol remarkably reduce the amount of entanglement which is needed to implement by LOCC. But LOCC plus entanglement cannot fully characterize separable map because for example, if we prepare one EBIT, we can achieve 9-state discrimination, but we can achieve control unitary. But this control unitary is not separable map, so entanglement plus LOCC can implement non-separable global map this area. So in that sense, I say that this combination cannot fully characterize separable map. So we propose a new approach to characterize the gap between separable and LOCC. So yes, and LOCC was the local operation, classical communication, and this classical communication obeys definite causal order. So I will explain what is the definite causal order in the next slide. And we define two new global quantum operation, class of quantum operations. One is LOCC star. This consists of a local operation, classical communication with indefinite causal order. And indefinite causal order is a bit stronger than normal classical communication. And it's not intuitive, but in the next slide I will say, but this indefinite causal order does not contradict with quantum mechanics so far. And the last class is LOCC star star. It consists of local operation, a causal classical communication. Here, a causal classical communication is fictitious communication, classical communication containing CTC, so I mean signaling from future to the past. And we obtain, we call them time resource, and we obtain such a result. So LOCC star contains LOCC and is contained by separable map. And LOCC star star, and overlap at the intersection of CPTP and LOCC star star is equivalent to separable map. And our result can be applied to n-parallel case as well. So, we can say that the causality of classical communication could fully characterize the separable map. So next, I will explain more precisely. So first, to understand the indefinite causal order, first we clarify the assumption underlying LOCC. So normally, causal order of local operations is partially ordered in LOCC, like 1, 2, 4. So I say that classical communication obeys definite causal order. So such a structure makes it extremely complicated to decompose a given separable map into LOCC. And please note that there are some research about LOCC where they use infinite round classical communication. But infinite round classical communication still obeys this definite causal order. So our approach is a bit different from their approach. And this is important. So is such a definite causal order a basic ingredient of nature? In some sense, no. Because indefinite causal order does not contradict quantum mechanics. So for example, consider two maps to whatever quantum instrument of completely positive and trace decreasing map. So if we assume definite causal order, we can combine them using such ordered quantum channel. This box represents some CTP map or some decreasing or whatever, or this order, or we can implement the probability mixture to definite ordered map. But I will give two examples of indefinite causal order. First one is a quantum switch. Quantum switch consists of two quantum maps and some quantum channel, which takes two inputs. One is control qubit and one is target system, and output is this. So note that the order of, for simplicity, I use unitary operation here, but so depending on the control qubit, the order of the operation changes here. And it is known that we cannot implement such quantum switch using a quantum circuit. So, I mean, we cannot implement quantum switch using definite causal order. But we can regard quantum channel as a linear, completely positive map from two maps into some quantum map. This this map is kind of this global map. And such that for any CPTP map, this output must be CPTP. So then this quantum switch satisfies this condition. So in that sense, okay, so quantum switch does not contradict with quantum mechanics, and so far I think nobody has succeeded to say that, prove that quantum switch cannot be implemented by quantum mechanics without the assumption of causality. And another example is quantum process, which is they use quite similar idea. So they regard quantum channel as a linear completed positive map to probability, such that for any CPTP map, the output must be 1. So if we use such a kind of quantum channel, we can achieve some classical task which cannot be achieved by quantum channel with different causal order. So in the both case, they propose a causally neutral formulation of quantum channels, and that leads, which leads the possibility of the indefinite causal order. So we use such an idea to our research. So let's move on to our setting. So first, we consider 2 local instruments depending on classical input. So Alice performs this quantum instrument, and Bob performs this quantum instrument. And we use the Choi-Yamekovsky matrix. We know that there is one-to-one correspondence between this matrix and this map. So we identify this CJ matrix as a map, and we use quantum instrument. This is the most general quantum operation, and like this. Okay, and Alice and Bob has quantum input and classical output and input, and we want to connect classical channel, classical input output with some classical channel. So if we consider only classical channel with different causal order, we can connect them in this way or this way. So in this way, y is equal to a. So then the total map becomes this one. So this is just a one-way LOCC, and in this way, the total map is this, and this is also one-way LOCC from Bob to Alice. So using different causal order, we can only implement a probability mixture of these one-way LOCC. And in our research, we use classical correlation, which is the generalization of classical communication. It is this. So, the classical correlation is the conditional probability satisfying this condition, and as we know, this is causally neutral formulation of classical communication, and then total map has this form. And we give 2 examples. One is here. So in this case, y is always equal to a, and x is 0. So that means y is equal to a. So that means Alice sends a to Bob. So it's classical. Okay. So this classical correlation represents classical communication from Alice to Bob. And in this case, this represents, this corresponds classical communication from Bob to Alice. And we define CC star. Okay, so which is the classical correlation that are consistent with quantum mechanics. So the precise definition is here. So we first define CC star 1 is a probability distribution. This one such that for any quantum instruments, the total map must be CPTP. This is the only condition for this one. So this one means corresponds to the fact that Alice performs only one local operation, both perform only one local operation. So if they perform sequentially perform 2 operations and 3 operations, we can increase this number, CC star 2 or 3 or blah blah blah. And let's compare this CC star 1 with normal classical communication. So normal classical communication from Alice to Bob, in general we can write down them into this form. So this means Alice's input and Bob's input depends on some shared randomness, pre-shared randomness, and Bob's input y can be it can depend on Alice's output. And then the intersection is shared randomness, having this form. And we can see this blue area is a mixture of one-way communication, a classical communication. And we can show that this mixture of one-way classical communication satisfies this condition. So we can say that CC star 1 is larger than this mixture. And we show that in bipartite case, this CC star 1 is exactly equal to mixture of one-way classical communication. So from there, we can say that LOCC star 1, that means local operation plus classical correlation star 1 is equal to mixture of one-way LOCC. So in this figure, we can say that such a and in tripartite case, we can show that CC star 1 is strictly larger than mixture of one-way CC, classical communication, and we can also show that LOCC star 1 is strictly larger than mixture of one-way CC. So in this case, we can say such a relationship. And we can also think about the star infinite. Then star infinite contains every infinite round called classical communication. So that must be larger than LOCC, and it's inside separable map. And we also define CC star star. It's a fictitious communication containing CPC. The definition is this: CC star star is a probability distribution. It's just a probability distribution. So using such a probability distribution, Alice can send her output into her input, or she can send her input to Alice, Bob's input, and Bob can send his output to Alice's input. And we obtain this result. The intersection of CPTP and this LOCC star star is equal to separable map for any tripartite system. And we obtain this result as well. So, assume one probability, assume one classical correlation, which is in the class CC star star, but not in the star 1. Then if we change the local operation, this is local operation and local operation, the total map can be non-CPTP map. So this orange area is the set of maps B and local operation generates. So this is a big problem because we want to characterize the gap between separable map and LOCC. But to achieve, in bipartite case, to achieve some separable map, which is not in the LOCC, we need this CC star star, because CC star 1 cannot generate any separable map, just a mixture of one-way LOCC. But if we use such a CC star star classical correlation, non-CPTP map can be generated. So this is a kind of a similar problem in the case of the entanglement. And we also show that this LOCC star set can be simulated by local process selection. Local process selection means they can select locally using just local operation. And so this is conclusion so fast. Okay. Okay. First, we derive this relationship in bipartite case, and if we want to characterize the gap between separable map and LOCC using entanglement, the good point is LOCC plus entanglement is always inside CPTP, so that's not in non-CPTP maps, but it can be non-separable global maps, so it can be this area. So that's another good point. And if we use CC star set to characterize the gap, the good point and bad point in process, and so it's always in this region, but can be out of CPTP. But we have these candidates as well. So in star n, so this corresponds to 2n round LOCC. This is always in non-CPTP, always inside CPTP and always inside LOCC star star. So it's always inside separable map. But so far we don't know this map can be any separable map or not. Okay, that's all. Very much.
Any questions, comments? Have you looked into SLOCC? Probably simulation is much easier.
SLOCC?
Yeah.
You mean we use SLOCC instead of LOCC star star?
No, I mean, where would SLOCC be in this hierarchy?
Okay, you mean if we consider the SLOCC, how?
Yes.
Okay. I think I think it's exactly same as the LOCC star star, I think, because up to some normalization. So because LOCC star star can be implemented by local process selection, and it's almost same as the SLOCC.
Any other questions, comments? That would be great. Thanks, Peter, again.